Good morning, everyone. Thank you so much for joining me. I guess I should say good morning, good afternoon, and good evening. I see we have some attendees from across the globe here today, which is absolutely wonderful. Thanks so much for joining us, for taking time out of the Astro schedule or just your busy schedule. My name is Shannon Holmes. I'm a medical physicist here at Standard Imaging, and it's my pleasure today to talk to you about the Exradin scintillators. I want to stop just for a moment before I really get into the meat of the matter today, and just say thank you to all of you for your work in treating cancer. We all know cancer doesn't wait on a pandemic. This is a critical care issue for so many people, and the work that you all do is absolutely necessary. So we are proud to be supporting you in that work. A little housekeeping as well before I really get into this. We are recording the webinar today. If you have questions at any time, please feel free to enter them into the dialog box in the GoToMeeting control panel. I'll try and answer those as they come in, but if I don't get to it in the middle of the presentation, I will certainly circle back around to it at the end. If you're not familiar with who we are, Standard Imaging is based in Middleton, Wisconsin. We're just outside of the capital of Madison. It's a beautiful sunny fall day here today. It's a wonderful place to be right now. But we've been in business for a little over 30 years. Started with some kind of humble beginnings with just a couple of products, but has grown to the point that we now design and manufacture a full suite of radiation therapy QA products. So with that, why would anyone choose scintillators? It's kind of an odd branch off to the side for those of us who are used to ion chambers and diodes kind of being the staple of the measurements. But with scintillation detectors, depending on the type of scintillator you pick, of course, you can get a water equivalent scintillator or a scintillator that is water equivalent, completely water equivalent for megavoltage photons and electrons. And the real key to this in terms of small field dosimetry is that you're not actually perturbing the beam interaction right there at the point of measurement. So you can use this to measure the dose in water without having to add additional corrections to account for the fact that you are changing those radiation interactions right at the point of measurement. Scintillators can be made very small, so you can get very good resolution, low volume averaging for the measurements that you make with them. The version that we're using has been shown to be dose and dose rate independent, which is quite nice because once again, you're not having to correct for these factors as you're doing measurements in these changing conditions of doses and dose rates. They've been shown to be energy independent. We mentioned that that kind of comes with the water equivalence of you. Because you're not changing those interactions, you're not showing variations in the detector behavior with the beam energy as well for megavoltage photons and electrons. They have beam quality correction factor of unity, which is rather huge if you've looked at some of the small field corrections that need to be made. It's no longer just the correction factor for your 6MV beam or your 6FFF beam and you're good to go for all your field sizes. There are changes in that beam spectrum as you go to small field sizes and therefore additional corrections that need to be made. But for our detector, those are our unity. We have a minimal temperature dependence for this device. It's about 0.1% per degree. So as long as you're measuring within the standard room temperature sort of QA measurements, you don't have to apply any temperature correction. If someday we take this to being a device that could be used for patient measurements, on patient measurements, then there may be temperature corrections that need to be applied. But we are not FDA cleared for that sort of use yet. So as of right now, it is just a QA device for that's used at room temperature generally. So you usually can ignore the temperature dependence. They can also be used with MR-Linacs. The scintillation fibers themselves are just plastics. There's no ferromagnetic material, nothing that is not MR safe in the detector itself. The electronics that you have to use to analyze it do need to be back from the MR field a bit, but the fiber itself can be used, of course, with the MR Linux. So our detector specifically is an organic scintillating material. Depending on which scintillator you get from us, we have a 1 millimeter diameter, 3 millimeter long active region with the W1 scintillator, which is the first generation device. With the W2, which is the more recent iteration of this, you'd get both a 1x1 and a 1x3 scintillator. So the smaller one obviously has better resolution. The larger one gets you a little bit better signal to noise ratio for the slightly larger, smaller fields that you're looking at. You do have to correct for Cherenkov light that is generated within the optical transfer fiber. This is one of the reasons that scintillation detectors have not really been widely adopted until now. The method that we use is a 2-channel chromatic correction based on a publication from Matthew Guyot et al. In Medphysics. The other thing about the scintillators is they're not absolute dosimeters. You can't send them in and have them calibrated and expect to be getting a perfectly stable response from them over the next 2 years. They do degrade as they get dose. So just like any plastic phantom you have that slightly turns yellow or discolors with age and with radiation, the same thing happens with these plastic fibers. And so it needs to be characterized. If you want to have your output in terms of dose, you would give it a reference dose and you can tie the output then to dose, but it needs a periodic recalibration as it accumulates dose. We see about a 2% degradation in signal for every kilogray or so, and therefore it does require that recharacterization, recalibration over time. That 2-channel chromatic method I mentioned is kind of graphically shown here. We have our scintillation curve on this side, and then the Cherenkov light is a broad spectrum light. And so we split the total signal up into 2 sections. We call this the blue channel and the green channel, or the blue and green portions of this spectrum. You would do a set of characterization measurements. In this image down at the bottom shows the characterization slab that we send with the W1. We have a smaller jig that can be used in a water tank with the W2. But essentially you would do one measurement with the fiber coming straight out. We call that the minimum fiber configuration. One measurement with the fiber wrapped all the way around. We call it the maximum fiber configuration. It's a 30 by 30 field for both of those measurements in this particular jig. You can do it in a 10 by 10 with the smaller one for the other fiber. But the idea here is that you're giving the exact same dose to the scintillator at the end of that fiber while changing only the amount of optical fiber that's in the field, so changing only the Cherenkov contribution. We calculate what's called a CLR, or a Cherenkov light ratio, based on the change in signal for the blue channel compared to the change in signal for the green channel. So on this plot, really, if you're just shifting up this Cherenkov curve, you can look at the difference in signal from one channel compared to the difference in signal from the other channel, and use that ratio then to correct subsequent measurements to remove the Cherenkov from this blue channel based on the signal that's measured in the green channel. If you want to give it a dose calibration, that's essentially just a scaling factor that goes on top of this scintillator signal. There's a question about, is there any reason not to use the W1 cal slab with the W2? No, there's no reason for that. You can certainly do it in those measurements in the larger fields if you prefer to. The W2 can certainly be used in plastic phantoms as well, but most people, when they're scanning, they want to be able to do their measurements in small fields, and so it's slightly more accurate potentially to be doing your CLR measurement also in a small field, just because you're even closer to the clinical measurements that you're going to make. However, you do need to make sure that there's a big enough change in the Cherenkov signal to have a good uncertainty on this CLR calculation, so that you're confident in those corrections that you're making. The other reason that we developed that smaller jig to hold the W2 is so that you could still do some of these characterization measurements on a unit like, say, the CyberKnife, that can't do a large enough field to cover this full calibration slab. Great question though. The W1 was the first generation detector. I mentioned that. It has been on the market since 2014. It only has one configuration, and that's the 1 millimeter diameter, 3 millimeter long active area. The advantage of this one at this point, it's been on the market for a while, but there are numerous publications available talking about the use of this and the output responses that people have had. One of the most exciting ones was the recent publication from the IAEA and the AAPM on small field dosimetry. This was the technical report series 483. Which has a bunch of tables listing beam quality correction factors specific to various beam energies as a function of field size. And so in all of these tables, the only device that's listed that shows beam quality correction factors of unity for the entire stretch of field sizes is the W1 scintillator. The W2 was not available at the time that this research was done. If you look for a few of the other detectors, if data are not shown, that means that the group was not, or rather the detector did not show a low enough uncertainty value that the group felt it was appropriate to be measuring fields of that size. The W1 was designed to be a single point measurement system. It was not really designed for scanning. But it requires a 2-channel electrometer, such as our Supermax electrometer, in order to gather both the blue and the green channel and perform that Cherenkov subtraction calculation. With the more recent device, the W2, we have improved the optics, and we have built a dedicated optics and electronics unit called the Max SD. To be able to take in that optical signal, perform the Cherenkov correction rapidly, but also to improve those optics and decrease the noise floor of the electronics so that we could go down to a 1 by 1 millimeter scintillator detector. The question, can you assume the same KQ equals 1 for the W2? Yes, you can. It's the exact same fiber, exact same detector. The only thing that has changed is the configuration of the electronics and the optics at the other end, really. So with this Max SD, the advantage is you're getting a higher signal to noise ratio. Part of the reason we provide this 1 by 3 millimeter scintillator is so that you can compare to those W1 publications, because that's exactly the same fiber as the W1. It just has an optical plug on the end instead of the shielded optics box. The other advantage of this Max SD is that it can take that Cherenkov corrected signal, convert it back into an analog output, and send it as a current to your water tank scanning electrometer. So you can hook this up, place this one, the fiber in your water tank. The Max SD stands between this fiber, of course, and your water tank electrometer. I guess I shouldn't say physically between it is, but it needs to set on the treatment couch or slightly away from the field just to reduce scatter to this device. But it processes the signal fast enough that you can collect the data then with your water tank electrometer and collect scans of these very small fields. If all you're doing is point measurements, you can do that directly with the Max SD. You don't have to hook it up to another electrometer. And in fact, you add some additional uncertainty if you do it that way. Just an example of one of those scans. This is from a publication from Paulina Galavis et al. This is Indra Das's group up at NYU Langone. And they compared the scanning with the W2 with a film measurement for a 1 by 1 field and got excellent match with that. They also just compared it with the W1 in terms of validating that nothing had changed with the fiber and got exactly the same results that we have with the W1 with no dose rate dependence and no dose dependence either. Another fun publication that came out last year came out of Richard Poppel's group, Jesse Snyder et al. And this was looking at variance hyperarc system and trying to measure the size or decreasing target size for single met treatments, and looked at the comparison of the W2 measurements with film compared to film for targets down to a 3 millimeter diameter target, which is the smallest one they looked at. And they saw excellent agreement between the W2 and film, and actually lower uncertainty on their W2 measurements than they had with their film measurements. So this is what they use now for their QA for their HyperArc system. So that's about all I was going to cover today. I know your time is precious. I wanted just to give you a quick overview of what these scintillators are, kind of whet your appetite for some of these small field solutions. If you want more information, please feel free to visit our website at standardimaging.com. The /welcome screen is our Astro screen, so there are other webinars scheduled through the rest of Astro, special webinars for Astro. You can certainly sign up for any of those you want. Even if you can't attend, you can get the recording sent to you. Or if you'd like to contact us directly, sales@standardimaging.com will get you to your sales rep if you don't know them. Or my email is sholmes@standardimaging.com if you have questions specifically for me. So with that, I wanted to thank you for your time here. If there are other questions, I'll take a look at those now. I see there's one that just came in. But otherwise, enjoy the rest of your day, enjoy the rest of the conference, and we would love to talk to you further in the future if you have any questions for us. So Eric asks, in the paper by Paulina Galavis, they saw a relatively large change when switching between parallel and perpendicular orientations. I do have a comment on that. They had one of the prototype units for the Max SD, and we discovered after the fact that they had a particular piece within the optics that had an anti-reflective coating on it that was colored compared to the clear that we normally get for that particular part. And so we suspect that the variation they saw, as well as the lower CLR value that they saw compared to the value of 1 that we expect for most of the Max SD units, came from that color change. Cherenkov has a slightly or has a preferential angle of production of 45 degrees to the travel of the electrons that are producing that light. And so if you are changing the orientation of the fiber from perpendicular to the beam to parallel to the beam, you can change a little bit both the amount of Cherenkov that you're collecting, well, A, that you're producing because you're putting more fiber in the field, but B, that you're collecting because of that preferential angle of production and the angle of travel down the fiber. So I also don't remember how that group did their CLR characterization and how much fiber was in the field for their max fiber configuration. But if there was a change in the color spectrum slightly, or if they just were generating enough Cherenkov to kind of swamp their signal, that also could have played into that factor as well. So we do recommend that you use the perpendicular orientation where possible, but the only times that we've really seen issues with the parallel orientation, it has been kind of linked to that that color change and the different filtration that we were getting from the lenses. That issue has been fixed, and that's something that, of course, we're checking for now when we get those parts in to make sure that none of the commercial units have that issue. I'm happy to stick around for a little bit more if anyone else has questions. Otherwise, thanks again for your time.